open discussion. And I see we have Dennis with us and we have Bob with us. Good morning. So if you would like to join us live in the conversation, just go to the link that I have listed there, which is live.naturalphilosophy.org, and I can add you to the program. And what I'm going to do is that we can take up to 6 people in basically my standby room here. And what I'm going to do is I'm just going to make sure that your audio can be heard. So if you want to speak, then just go ahead and break in when you can. We used to do this with Fuse, where we used to have, you could raise your hand and I would see you and I would know to put you on. But in StreamYard, it's a little bit less obvious. So Dennis, if you want to go ahead and just say anything, then please do, as well as Bob. So we've got us 3 here.
Hey, Franklin?
Yes.
Okay, you can hear me. Great.
Yeah,
I'm trying a new headset, new mic, and so forth, so it's good that you can hear me. Now, I am trying not to go and use this live.naturalphilosophy.org because of the restriction of only up to 10 people, so I didn't want to take up that bandwidth. So I'm out on, as well, the YouTube and John Chappell Natural Philosophy website and the other 2 links that you provided, and I'm not seeing anything.
Well, you should see it now. Let me go and check to see that we're actually alive. I'm going to go to youtube.naturalphilosophy.org, and the link won't show up until we're actually live.
I'm wondering if there's, okay, now it's showing that there's a live thing.
Yeah, live now. So that's what happens. See, unfortunately, that's another thing compared to Fuse, in that, if I come in early, for 15 minutes early, which I typically do, people can see and immediately join. With this StreamYard, you don't see the live feed until I actually click that we're live.
Okay,
so
super.
You really have to wait, and I'm kind of wondering whether, maybe we might be losing some people because when they go to the YouTube channel, they don't immediately see us live. But I am trying to get us turned on right at 7 a.m. here Pacific, so that anyone joining will come.
Okay.
But
so I'm out on the YouTube.com, and I'm trying to see where I can enter a comment, and it says on the right-hand side, top chat. It says, "Welcome to live. Remember, you guard your privacy." So down below it says, "Say something," and when I put my cursor over that, it says, "Sign in to chat." Sign in to what?
Well, I think you have to be a member of Google.
So you have to join something. I mean, it's not just out and available on the website. You have to have an account, sign in, etc., in order to participate.
Yeah, I believe that is the case. Yeah, you have to have a Google sign-in.
You should mention that in the promos or in the emails that you send around, reminding people of the weekly meeting, because the weekly meeting seems the meeting notices that you've been sending out seems to suggest that you can participate simply by going to this website. And apparently you can't. You can sit and watch, but you can't participate unless you have an account. And I think you ought to say that explicitly. Just a thought.
Okay. Yep.
And now I'm back to the StreamYard.com. And on the right-hand side, there's a private chat and live comments. Which one do I use to interact with everybody that's here?
Well, I think that, let's see here, comments. Yes, in the comments, those only come from YouTube or Facebook. So if you are on YouTube, Facebook, I can see those comments. But since you're here in the StreamYard, you would have to use the private chat. So since you can't really enter any comments in the comments section, so. And I have to actually see you to see it, and I have to click over there since it's not 100% obvious when you type something in. So like,
Yeah,
I'm gonna put something in the private chat.
I'm wondering if I'm on the Facebook or the other YouTube and I type in a comment there, where is that going to show up here? Under private chat or under live comments?
That would show up under live comments. So let me go ahead.
So I kind of have to switch back and forth between private chat and live comments in order to get all comments?
I think so.
Strange. Okay, thank you.
So I just said, I just sent a comment from YouTube.
I see that under private chat. This is a private chat. Yeah.
Yeah. Now I just sent a comment from YouTube, but I don't see that comment. Okay. Then it took me a few seconds to see that comment, and then when I see a comment from YouTube, then I can click on it and I can show it. So that's what a comment from YouTube looks like. So if someone wants to make a comment, I mean, I still have to moderate and choose to put it up, but I can see that.
Okay, just trying to get used to the new system. Thank you.
Yep. And hey, look, we got 6 watchers now. Okay, great. Welcome everyone. So we've got like we got a couple people in StreamYard here live. We got Alistair as well. So we've got 5 people. We've got well, back down to 4. Something happened to Bob. Okay, I guess Bob exited to just watch us on YouTube, which is great. But all the rest of you are added to the stream so that you can talk if you'd like, and then it'll just be like views, right? So like I say, hey Bill, how you doing?
Fine. Takes a while to get used to the new system.
Yeah, you get used to the new system. So today is kind of an open discussion. So I was wondering whether you have any topics of discussion. Otherwise, I was going to do a little thing called the mailbox, and I was going to start answering replying to some of the emails that I've been getting. So you have any topics on mind here?
Well, I'm working on a series of papers for the Common Sense Science newsletter on the quantization of gravity, but I'm not quite through to the point where I'd like to do presentations on it. But I have 5 papers that are going to be on that topic, and I should be through sometime in early 2020, and then I'd be able to give some interesting presentations. The thing that is significant in those talks is that I talk about the scientific method that we use and how we have changed that in the last 150 years twice, and both times we're removing more and more of the role of logic, so that a logic cannot falsify a theory. And then when I do a new theory of gravity and talk about the quantization of the orbits of the planets about the sun and the moons about the planets, and an additional 2,600 planets that we have made measurements on and other stars nearby, we see that our current theories don't do too well, and the new theories can explain all the data that we see. And not only that, we don't need dark matter and dark energy and a whole bunch of other phenomena that we were able to describe, like the expansion of the Earth. Why is the Earth expanding? And all of that is related to the theory of gravity. So those things are coming up, and they'll make interesting presentations, but I'm not quite ready. I like to have a good formal PowerPoint so that everything is well organized and that sort of thing. But I'm not ready today to do that.
Okay, but that's always an interesting topic, which is, why are the planets spaced the way that they are? So you're saying you've got a bunch more data to support, I guess, the quantization of gravity. Although I'm from an empirical standpoint.
The first law for quantization of gravity was before we had Newton's work. It was Bode's law, and it worked on all of the planets that we knew about at that time. And then as we discovered more and more planets further out from the sun, we found some that didn't fit that quantization law. And so that was the problem. And then we started doing the moons about the planets, and we found, well, a lot of the moons about the planets fit that quantization law, but some don't. And why don't they? But no one's been able to derive Bode's quantization law. You can't derive it from Newton's universal law of gravitation or Einstein's general theory of relativity. And so something is wrong. And the person who had the solution or knew what to do was a fellow named Henri Poincaré, and the one that extended the what we call natural philosophy to include meta theory, and he derived a number of theorems in meta theory which apply to all areas of natural philosophy. And basically, he showed how to use logic to improve your theories, and if it's possible, to even obtain a universal theory. So those are some of the areas that we're working on trying to complete. But of course, it's a lot of work to complete all the science as one universal theory, as you probably know. And so you do a little bit at a time. Maybe you take one field like gravity or the force of inertia or the origin of life or, the atom, the theory of the nucleus, theory of elementary particles, all those things you got to be able to explain.
Yeah, I think that is, of course, the holy grail of physics, which is to boil down everything that we see in terms of something which is fundamental, simple, or something. At least that's certainly what I am trying to do with, say, my own theories, where I literally try and boil everything that we see down to just the presence of the electron. So just given you have some particle, you can derive everything is what the goal would be.
Yeah.
And that's kind of the idea of the monads and the antimonads, which you have mentioned. That I think is also kind of very similar to just the idea that only positrons and electrons exist, and then try to explain the entire world out of those things. That and I try not to use anything other than, say, Newtonian mechanics. So things which are macroscopically observable. But so I was wondering, so is there something, so how do they make the planets that don't obey the Bode's law work? I mean, do they obey a kind of Bode's law, or is that just counted as an exception? Or how are those ones that don't obey Bode's law accounted for?
Well, you need a little background there, and that is in meta theory that Henri Poincaré did. He derived a number of theorems, and those theorems will apply to gravity, to many areas. So one of the theorems says that you cannot have a unique fundamental force, or two unique fundamental forces that are 1 over r squared type distance dependent. But electrodynamics and gravity are both 1 over r squared. Gravity is 10 to the minus 40th power, as strong as the electromagnetic force. It's very weak, but it's still the theories we have, both Einstein's general theory of relativity and Newton's universal law of gravitation, both are 1 over r squared. So what Henri Poincaré said was, since electrodynamics is that way, and also if you look at general theory of relativity, the formulas for gravity involve c, the velocity of light. And so Henri Poincaré said, well, it looks like everything has to be, both gravity and electrodynamics have to be electrodynamic, because you can't have a fundamental constant of one fundamental theory involved in a second fundamental theory. And so that's what he pointed out. So that was one aspect. Another aspect is when it came time to making the theory of the atom, we started out with the Bohr model. And the Bohr model is also known as the planetary model. And that is, we knew there was some kind of quantization of the orbits of the planets about the sun and of the moons about the planets. And so we used that as our beginning first attempt to describe the theory of the atom.
Which is wrong.
But the theory of the atom has progressed. And now we can predict the newest theories of the atom. We can predict the properties of the atom to 8 significant figures. And that is quite significant. And the theory is a little bit different now than the theory we had for the planets. And so the idea is to take the current theory of the atom and use that as the prototype for the theory of the gravity, and see if now if we develop a similar theory to the atom for going backwards to the solar system, can we now predict all the properties to 8 significant figures like we do for the atom? And the answer is yes, you can.
Yes, you can. Boy, I have just a moment, Bill, but I have some comments about that idea. I mean, I think that we saw that the planets went around the sun was a very appealing idea for supporting the Bohr model, which is to think that, well, if the planets can go around the sun, then the electrons can go around the nucleus. And while I think that's just extremely naive, actually, really. But I'm thinking that is probably one of the worst scientific blunders of all time, because I don't, say my particular model of the atom doesn't have anything orbiting. I mean, you can see how like maybe 7 planets could orbit around the sun, but how can 92 electrons orbit around uranium atom and in any way, shape, or form, keep these stately orbits? I mean, that's just not plausible. Probably in anyone's mind. But
it's more complicated if one starts thinking about complex atoms and molecules. How can these orbiting electrons allow all these atoms to be connected in a big, say, organic molecule when they're all orbiting, and then how can they maintain the stability? And so what you discover is they can't be orbiting. And also the laws of electrodynamics say that if you have any charged particle that's orbiting something, it must radiate continuously. And in every experiment we do with accelerators, that's what we see.
Yeah, well, I think, we both agree that the electrons really aren't orbiting in your theories and mine. We think that they're statically located. But, you just said that that we can say model gravity like we model the orbits of the electron. So
No. I'm saying that the best theories of the atom, including quantum mechanics, uh, they don't so much have the electron orbiting. They have, like you think of quantum mechanics, they have the universal wave function. What is that? Well, they don't have it. Something that's real physical that we can talk about, but it is what predicts what you can see. But in the case of my work, for instance, the fundamental thing in the universe is the electromagnetic field, and the source of the field is not particles. Particles are just solitons in the field, and
but that's where we would disagree.
Yeah, we would, because
I would disagree. I would say
particle-based theory.
Yeah, well, my field is I mean, definitely the electromagnetic field is there, but my disagreement with you is that I start with the particles and I say that the field is built out is an emergent property out of that field of particles. So the electromagnetic field is emergent; it's not fundamental, which it could be. I mean,
and yet we see the electromagnetic field controlling galaxies, our solar system. We see huge currents coming down at the poles and going up from when you have a thunderstorm or something like that. We'll often see lightning from the surface of the Earth go up through the cloud all the way to the sun. And so, why is all that going on? And it's kind of continuous, and we see the aurora borealis and all that kind of stuff, with these currents coming down.
Well, none of that is relevant to this base question of what's fundamental, I suppose. I would say
remember,
that.
I told you that the force of gravity is 10 to the minus 40th power as strong as the electromagnetic force. So if the electromagnetic force is continuously coming down on the Earth and the Moon, it's exerting more force than gravity could ever exert. And so we gotta somehow account for that. And what we do when we have our theory of gravity, the separate theory, like Newton's universal law of gravitation, we ignore the electromagnetic force. And but it's so. I mean, do you realize what 10 to the 40th power is? How strong is that? It is just overwhelming. And so that's what we've gotten away with ignoring that in the past, but we're starting to see it more and more as time goes by.
But people ignoring the force of gravity or the force of
no, ignoring the electromagnetic force of the sun on the Earth and the Moon and the other planets. It's dominant. It's not a little bit dominant. It's dominant by millions and billions of times. And so that's what we need to take into account somehow. And
well, I mean, you were mentioning the difference in strength between gravity and the electrostatic force, and I was like at a lecture, and the guy basically said that if instead of having ordinary mass, that I was just like a ball of, like, say, electrons, that the amount of force that would create would just like suck the entire room into that into him. That's how strong the force of just the pure electrostatic force, right? If you replaced all his atoms with just like one electron, so that he was just like all negative charge, right? Then it would create a gigantic force. But on the other hand, I think we both agree that gravity is an aspect of the electrostatic force or field, right? That it shares much of the same characteristics.
It's not the electrostatic force; it's the vibrational force that is occurring in uh, elementary particles and atoms.
Yeah,
So you think
that
of
would
they
be
have
another area where we would disagree. So in your theory, the gravity is caused by the vibrations of, say, the atom, and that creates basically an electrostatic imbalance, I would say. Fundamentally, I mean, I've seen other equations where they calculate, well, if the electron is moving around and the positive charges are staying stationary, that creates an asymmetric situation, and you can kind of calculate that there's going to be a net attraction of the negatives to the positives. I've seen that. That's also another way of doing electrostatic gravity. Although you, in particular, have to rely on the oscillations of a particle, so that somewhat depending upon, say, the heat. This is why you like to relate heat to gravity, right? That's basically the energy source for gravity. I would suppose the more that it's vibrating, the more that may change the force.
We have a whole lot of data that you're not considering yet. One is that using the vibrations of dipoles, quadrupoles, octopoles in atoms, where you have the vibration of the electron with respect to the nucleus, what you find is that you can derive the force of gravity, and you can predict the value of G. Not fit the value of G, predict it. So it's no longer a fundamental theory because you can predict it. And you can predict it, gravity, so accurately that you don't need dark matter and dark energy.
Well, gravity is kind of a slippery thing, because if you can precisely predict the gravitational constant, then you're wrong, because it appears that the gravitational constant isn't constant. This is the frustration that everybody has. You have 10 different experiments, you get 10 different values.
We predict the temperature dependence of gravity.
And there might be a temperature dependence, but you can't predict a singular constant G. What you should be able to be, well, like you said, if that's true, then you should be able to take these experiments and say, okay, re-perform them, but perform them at 100 degrees, and then perform them at 50 degrees, and then perform them at 0 degrees. And there should be a difference. That should change the constant, the constant of G. So, because it just seems that G is not a constant.
Mass changes with temperature. So
we have some evidence that happens as well.
The problem with many theories like gravity is what is gravitational mass, what is inertial mass. They're not defined fundamentally. They're just defined as a constant in an empirical equation. And
yes, well, that's why I think it's advantageous to think of gravity as, say, an emergent property based on some other fundamental property. So if we think that gravity is an emergent property of the electromagnetic field, which I think probably both of us would agree on that it's some aspect of the electromagnetic field. But fundamentally, the thing that's actually driving things together in gravity is, in fact, the attraction of a negative to a positive charge. That would be kind of the ultimate statement of what at least what we can agree on. But we do disagree on, like, say, the mechanism, but it's a little bit hard to tease apart what the mechanisms would be. So, like I said, I described at least 3 different possible ways it could work. We have your way, which is it has to do with the vibrations. There's another way which just has to do with the electrons orbiting around the nucleus, and that causing some indifference. Or it could just literally be in my case, gravity is due simply to the charge displacement, that the Earth is just a positively charged ball, And that alone is causing us to be attracted towards the center of the Earth as neutral matter. So that's a dipole argument, that if you have a big charge over here and you have a dipole over here, the dipoles will end up pointing towards that charge. They'll be aligned. And because this one charge is a little closer than the other charge, that causes an imbalance, which causes the pole to be actually dragged towards the charge. So now I like that because it's simple, right? And it can be demonstrated. When you take your comb and you rub it in your hair, you can attract matter. I mean, large pieces of matter. Like if you put a coin on the edge, you can attract that. I mean, it appears to attract everything. It's similar to gravity. And that is clearly just matter being attracted to, neutral matter being attracted to an electrostatic field. So that can at least be macroscopically demonstrated. And for me, those kind of demonstrations are interesting and provide more evidence than say the explanation that electrons are like orbiting around the nucleus, because then I would ask, well, how does that happen? Once again, we were asking about, how does it seem even remotely conceivable that these electrons could be just like flying around this tiny little nucleus? And that's another question. How can all the positive charges be stuck in a tiny little spot and not blow up? And what is the purpose of the neutrons then? We have there's like half neutrons and half protons in there generally, and like, what are they doing there, right? What is their purpose? How do they glue the atom together? And
did you realize that the evidence for neutrons in the nucleus no longer exists?
Well, the evidence that you're showing is that the neutron does not exist as a unique separate particle, that there are no non-1 over r squared forces, right? Precisely, that's what it's saying, is that you can probe the atom and you can look for the forces that are holding it together. And, the experiment that you're citing there says that the only force we can find inside the atom is 1 over r squared, right? And that there's nothing, like if there's anything binding that neutron together, it would in fact have to be 1 over r squared, because there's no 1 over r cubed forces, or, to the fourth or the fifth, or anything that responds to a strong force, right? There's nothing.
We measured the mass of all these 3,500 nuclear isotopes, and we can plot all of them with the same atomic number. We might have as many as 20 or 25 different nuclear isotopes with the same atomic number. And so what's going to be different between these is the number of so-called neutrons that are inside. And what we find is that the plot doesn't show that there's any binding energy at all.
Yeah, there's no binding energy. At least no special binding energy.
See, a neutron has binding energy. It has 8 MeV binding energy. If I can measure the mass of the nuclear isotopes to 8 significant figures, I can measure the binding energy of the neutron to 4 significant figures. But it comes out to be 0, the 4 significant figures. And
yes,
so
it's
that
0.
means
there's nothing.
There's no neutrons there. There's no particle called a neutron. And
No,
the neutrons
I would disagree with that.
Supposed to interact with the protons and the other particles with the weak interaction force and the strong interaction force. And those are 1 over r cubed and 1 over r to the fifth. And there's no evidence that there is any such forces in the nucleus anymore, because now that we've measured 8 significant figures, there isn't any. To 8 significant figures, there is no such thing as a strong interaction or weak interaction in the nucleus. And there's no such thing as a neutron in the nucleus. There is a particle called the neutron, but it doesn't exist in the nucleus.
Well, I'm going, yeah, that's absolutely right. There's no strong force. There's no weak force. And experimentally, we now have evidence to say that the strong force is a pile of, it needs to go to the trash bin, really. And the strong force was a ridiculous force anyways. It's just like the strongest force in the universe when it's within the diameter of a of a nucleus, but absolutely zero everywhere else. And we don't know any, I mean, logically, that doesn't make any sense. Plus, that still doesn't explain what the purpose of the neutrons is. And I would say that the neutrons and the protons are really all held together still by just the electrostatic forces, the only force we've got left. And I would say that they are there, and they're just there as a positron electron pair, as a dipole. But in my theories, I actually came up with a paper that explains how mechanically that dipole is necessary to connect the proton. So in a geometrical way, I explained that it's actually the neutrons which hold the atom together. They can hold a proton chain together, is how I explain that. Since I have a very specific physical model, I'm famous for the Lego brick. This is the cubic atomic model, and if you were to get a really, really powerful microscope, and someday this may happen, that when they actually look at an atom, that it may look something like this. It's got 4 arms, and 6 poles, which explains the 6 possible docking ports for an atom to connect to another atom, versus the conventional view, which is that your atom is like this tissue paper, and it's got like the electrons flying around in every which way, and somehow 2 of these things are supposed to geometrically attach to each other. That just seems ridiculous, right? I think it's a lot easier if it was more like a tinker toy kind of thing, or just going back to your chemistry set that had the balls and the rods, right? I mean, those are actually very accurately represent how we think atoms connect together in their chemical reactions. And literally, they're like this. You have something that can act like the stick, and you have only certain angles which you can work with. So, but that's just an interesting part of I think of my work, that I can explain why the neutrons are actually there, and why you need them in order to connect the protons together to build like these really complicated atoms like uranium. So it's a necessary part. But I would say that the neutrons are there. They're just a positron-electron pair. But when they are ejected from an atom specifically, then they do have certain properties that they basically don't have when they're embedded inside of an atom. So we can observe that they have a certain, that they can decay. And I think they're trying to determine what the binding energy of that thing is by those decays, but it's kind of a backwards thing, because I'm thinking that if it's just a positron-electron pair, that thing can't decay. Okay, that's basically the same thing that space is made out of. What it actually has to do is it actually has to run into a particle space. So I also think that there's no difference between the neutron and the particles that make up space. I mean, essentially, I think space is a neutron sea. The neutrons being just these positron electrons. And what happens in neutron decay is it has to be going at the right speed to actually hit another particle head on and join together, so that you have 2 positrons and 2 electrons forming a new particle. And so what will happen there is that 3 of the positrons in that group will form a new proton, and then it'll kick out the spare electron. So I would think that neutron decay actually isn't a decay. It's actually a reaction with an outside particle. Now I see that we do have a bunch of comments coming on here, so let's go review some of the comments here. So we've got something from Michael Antesky. And so it says, vibrations are non-directional. Gravity and other quantized forces are vectored fields, directional. So I guess that one's directed towards you, Bob. I mean, Bill. Vibrations are non-directional.
In my book, I derived the force of gravity, and you realize in an atom, you've got electrons in shells, and you've got the protons in shells in the nucleus, and they have spherical symmetry, except for the most outermost shell, which isn't full, won't have spherical symmetry, but the rest do. And so most of the atoms that are contributing, you could have to average over all the directions to see what the net result is going to be. And so that's what we do there. And also, what was I going to say? Oh, on your theory of the with all the things being made of electrons and positrons, you need to be able to predict the 96 observable elementary particles that we can make beams of and perform experiments with. And
yeah, I can totally do that.
You need to be able to explain the mass, the 8 significant figures, that's how accurately we measure it. You need to be able to explain the spin, the magnetic moment, the total charge.
Give me a couple of grad students, I'll do that.
And all the decay modes. We've already done that for the model I have. And everyone who worked with me on that lost their job at a university for having published such a paper.
Good thing I don't work for a university.
Validate these other theories, and those are the politically correct theories, which don't the scientific community does not want to be invalidated.
Although getting back to Michael's comment here, so he's saying something about vibrations not being directional. Now, I know you're saying something about spherical symmetry, and I would say that vibrations are highly directional when you've got that spherical symmetry. Like if you have a bell and you hit it, the vibrations are definitely heading out away from the center of that bell. So I would say that they are, in fact, highly directional. So I don't know that that is a particular objection to either of our ideas, I suppose.
Dipoles are directional.
Yeah, I'm just saying there's a lot of directionality here. I mean, if the objection is that that gravity couldn't be due to a vibration, I would say that no, that's not right, because if you have an atom and it's vibrating, then it will send out its vibration in a highly directional outbound direction to all of space, right?
See, Michael says a general term, vibrations are non-directional. Well, every type of vibration, like a dipole, quadrupole, octopole, they're a little different. But they have certain symmetries and that sort of thing. And we've already measured it in the laboratory. We know that we have confirmed that. So to say that gravity is a vector field, 1 over r squared for the force is not a vectored field.
It's not. I would say it's totally vectored.
Well, the thing is that
see, I could represent gravity like this. See, there's one end, there's the other, and it points to the center of the Earth. That's vector. It's got a magnitude and a direction. So that's what we mean by gravity. So, and if I drop the pencil, it follows that vector. So I would say that's totally fair. Yeah, gravity is definitely a vectored field. I mean, just like electrostatics is a total vector field. That's how we represent them, as like lines and arrows, and that's how we represent them.
But Steve, let's take the gravity of the sun. If I look at the planets in all different directions, they're all simultaneously experiencing it. But if gravity was directional, that wouldn't be the case. They wouldn't have that same result.
Why? I mean, they totally would have the same result. They're all pointing towards the sun.
No, they're pointing towards the sun, but it's a different direction for everyone. How can the sun's gravity be going in all these different directions simultaneously if it's a vector field?
Well, that's exactly what vector fields do around spherical objects. Like if I have a spherical object here, the force would be going around like this, and it continuously changes depending on, where you are from the center of this thing. That's obviously, that's the way a vector field around a spherical object works. It goes directly out from the center out to every single point everywhere around it in a spherical space, right? So yeah, it's different everywhere.
But see, that force between the planet and the sun, they're all directional, if you know what I mean, a different direction.
Yes, and it has to be a different direction. It's every time you move to a different place, you're intercepting a different. It's like if the sun, you just considered its light, right? If you just considered instead of the gravity, you considered its light. Everywhere you look, you can see that the rays of light are coming from the sun, and if you're on the Earth, it's coming from this direction. If you're on Mars, it's coming from that direction. If you're on Saturn, it's coming from that direction, and it's all perfectly logical that it's all coming from the sun at different directions. Is it? It's kind of a trivial point to me.
But for instance, if I have just one dipole, it won't produce gravity in all these directions. Did you realize that?
I don't think individual gravities dipoles create gravity.
Is the dipole is just going back and forth like a spring, and a spring, if it's going back and forth, it is not going to be in every direction. It's only going to be in one direction. And so each of the individual dipoles are in one direction, but all the dipoles are spherically, in atoms, are spherically distributed in the shells of the atom, so that the net, if we had all the shells complete, then the net force would be zero, basically, because it would average out. When you summed over all of the dipoles to see what the vector result was, you would find that it averages out to zero. So you have to have some irregularities in the spherical symmetry in order to have a net force of gravity.
Or if you just think that it's an electrostatic force, then you just have to have one electron fall off the atom, and then that would create a net force on that the atom is providing. And that's why I think that's a simpler idea.
Another problem we have to direct is Kolwick, the University of California at Berkeley, showed that the electromagnetic field is continuous, uncuttable, and has tensile strength.
And I would agree with all of that.
If the source of the electromagnetic field is particles, that's never going to be the case.
Well, you have to that's totally the case. If the source of the electromagnetic field is particles, and that the electromagnetic field is perhaps, I consider it like a wave phenomenon hosted on particles, then certainly you're going to get things like, you cannot cut a wave, and you get tensile strength because there are physically particles from any given spot to any other spot. And
if I have some particles that are producing the electromagnetic field,
but particles don't produce. Particles don't produce the electromagnetic field. Particles mediate the electromagnet. The electromagnetic field is emergent upon the particles as a wave phenomenon, is how I see it. Gravity, the electromagnetic field does not. Well, it's almost silly to say that it comes out of a particle, because only millions of particles in concert can host an electromagnetic field. a single electron by itself can do nothing. You could probably measure no properties of an electron.
Oh, that's not true.
No, I
We
mean, it's
have a
not
way
true
of-
because, but I'm talking about like
We have a
totally
way of-
isolated.
We have a way of putting one electron in a.
Yes,
what
I
is
know you
this?
do that, but that's still immersed in a sea of other, like I say, neutrons. You have to consider that anything that you do is immersed in a sea of neutrons, and that all the emergent effects that we get are due to that neutron sea. So, and I think it's just a little bit easier to talk about a neutron sea because neutrons are something that people, even mainstream recognizes. If I keep on saying that they are a positron electron combination, then people get all bent out of shape because they think that positrons and electrons annihilate and that shouldn't exist. But if I say that everything exists in the sea of neutrons, and it's actually say the interaction of that negative charge with that sea of neutrons is where we get mass from. But let's see, we've got some other comments here. So we have David de Hilster. So David says charged particles are a convention, not a physical reality. What do you think of that, Bill? Are charged particles a convention?
Well, I've performed many experiments in accelerator laboratories, and we don't agree, the experimentalists don't agree that charged particles are a convention. Now, it is true that in the standard model of elementary particles, which has 450 elementary particles, more than the 96 that we can perform experiments with and form beams of, those particles are dependent upon theories. In other words, if a certain theory that you're trying to use is going to have to describe it, we have to invent more particles because we can't describe it with what we got so far. And so it's like when Einstein's theory of general relativity couldn't explain all the details of gravity, we invented dark matter and dark energy to supplement it. That's what they do in theories of elementary particles, is they invent more particles to supplement the particular theory of elementary particles so that they can explain it, but you don't have an experimental verification of that particle. You have an experimental verification of the results you're trying to predict, but you don't necessarily see that particle there.
But what about the basic particles, like an electron?
Right.
Is an electron a convention, or is it a physical reality?
That you can form into beams and do all kinds of experiments with those particles. And so there are 96 of those. So my feeling is that any proper theory of elementary particles should be able to predict the existence of those 96 elementary particles that we already have confirmed experimentally. The rest of the 450 elementary particles, we have not confirmed experimentally that they exist. We have only said that if this theory that of elementary particles is going to work, we need to have these elementary particles, but we've never seen them.
Yeah, that's like the W and the Z boson, right? That's an example of a particle which we cannot form a beam of those things, and they're highly dependent upon theory to give them the characteristics that they're actually experimentally measuring, right? Because in the accelerated experiments, they do their calculations and they say there should be this particle existing at exactly this mass, and they go out and they do the experiment and they go, aha, based on all these decays. They don't actually have an example of the actual W particle because it only lasts like a billionth of a second, theoretically. That we have this, that there must have been a progenitor particle, which is the W particle, and they say, yes, we found it. And, same thing with Higgs boson. That I wouldn't say that's a convention. I would just say that that's a lie. So,
well, For my PhD thesis, I worked at the Space Radiation Effects Laboratory called Chappell, and we made beams of electrons, muons, kaons, ions, and from those beams of particles, we made atoms.
Yeah, so those are
So we
physical
made
reality,
atom,
right?
a muonic atom, a kaonic atom, and we then measured all of the energy states, emission spectra, and absorption spectra of those atoms, and that was what my thesis was to show how we did that and how we were able to predict the results coming from those atoms, which were different from an electron atom, and because these other particles, although they have the same plus and minus charge that electrons and positrons have, they have quite different mass, and they also can decay. And so you've got that process going on too, whereas electron and positron don't decay. And,
yeah, well, those things, though, the electrons and positrons, I would definitely say are a reality, right? As real as, you know, this calculator in my hand is real, right? That's not a convention. I would strongly say that charged particles are very much part of our reality. I guess we have the next comment we have here is this one from Michael. No, let's see. No, that's not it. Now he's saying something about ether continuing carries quantizing forces into intervening space inside the gravitational bodies. I think that may have been a comment on that. Let's see here. But we have directly a comment from Stefan saying, hello, David. Then what is then reality? You say that particles are not reality, but we use particle model to predict things. So what is reality? And that's kind of like the point of all the things that we do know. We have been able to isolate things like protons and electrons and definitely neutrons. And just with those three particles, we can build up all the atoms that we know about. So, and that, you know, the stuff that makes up, you know, the physical stuff that we can hold. So, and so I would kind of disagree that you know, particles are a convention. And of course, David, if you would like to come on the show, and you know, in addition to give comments, you can always come on the show and join the conversation here with me and Bill and Dennis. Then please come on to live.naturalphilosophy.org right now, and you know, we can chat live interactively. So let's see, but that was, I believe, our comments so far here. Let's see. No, we've got more comments here. We've got a question from Duke Nucleon. What encodes the any field? So I would say, though, let me see. So I think Bill would say fundamental, therefore requires no encoding. Would say, Bill?
Yeah, I'd say that the universe consists of the electromagnetic field, and that all matter and particles and everything are resonant structures called solitons in the field, or monads. And that idea goes all the way back to Moses and the ancient Egyptians. Their idea of the atom was based on Moses' idea, and of the monad, and we have that view. Of course, the source of the electromagnetic field is God in that point of view, and so the way that God creates is He ripples the electromagnetic field to make various types of solitons, and then they form structures, and that is how you have matter. And if you look in the book of Genesis, where it gives the beginning, you know, the first thing that you get is the field, and you get light, which is waves in the field, and then you progress on to various kinds of matter. And so we see that, and that used to be taught in our schools in America until about the year 1850, when what we call the wall of separation between church and state was interpreted in such a way that the government could determine what's going to be taught in school, not individuals. And before that, the parents who hired the teachers and built the buildings for their school in their neighborhood, they controlled what was being taught. And but that once the government became responsible, they didn't care what the parents wanted. They did what they wanted. And so that's how we see various theories coming about, not because of logic or verification, but because of other ideas that they were concerned about. And it looks like, if you look at James Madison and Thomas Jefferson, and why did they create the wall of separation? It was to satisfy three different groups and political groups in the United States, in the colonies, I guess. And a lot of people did not like religious activities going on. They had what was called the First and Second Great Awakening, with all kinds of revivals going up and down the coast of the colonies, and many churches being founded, Baptist, Presbyterian, Episcopalian, Methodist. They were being founded, and they exceeded the number of people in the state-sponsored churches, the established churches. So with the wall of separation between church and state, every colony was asked to remove its support of an established church. And so they did. So, for instance, I'm coming from Maryland.
Duke has a follow-up question there.
Yeah.
He's saying, is the field just magically there at every point?
The field is an emanation from God. It's a part of God. And that part enables him to create matter, and to perform all kinds of what we would call miracles and things of that sort. If you and if you look in electrodynamics in the history, before 1850, what did they call what we now call the electromagnetic field? What did they write in their writings? They said it was the Spirit of God. That's what they put.
Yes. Well, with all due respect to God, you see, I don't think that we actually need to appeal to that. Now, I think that God is totally involved, but I think what he created was the electron. Okay, I think God created the electron, and he made it vibrate, and then he made it vibrate in the opposite phase, and that's the only two things he created. Because I think God doesn't want to be responsible for creating fields and gravity and all that other stuff. I think he wanted to create the simplest thing he could possibly think of, which is the two particles, which are actually exactly the same, but could be differentiated by some kind of phasing of some sort. So, I mean, the question here that Duke was asking, which I think is a very important question, which is, what encodes any field is a very important field. So we're talking about electrostatic fields, we're talking about gravity fields, we're talking about magnetic fields. And the one thing that all those fields have in common is that they can be represented by vectors. So like gravity, like I was explaining, it's a vector field, which has a specific direction, just like, and it can point in any direction in space, and it has to have a magnitude. So I think what Duke is talking about is basically what encodes this vector, right? I think physically there has to be something that represents this physically, right? It's not a concept in God's mind that causes this, because God doesn't want to be responsible for every point in the universe. God would rather have his universe take care of itself. So I think that's an important question. And I mean, I can provide what I think, my answer is to what encodes the field. And that's, first of all, starts off with, you need a physical medium in order to have a field. So I pick a particulate medium. I pick a sea of neutrons. So that's what I do. First job one, in order to have something that can physically represent a vector, is to physically put something that can have a vector in it. So a field of particles is a start, right? So you must have something physically there. So now the other question is that you have something that can support a vector, because you can always draw a line from one particle to the other that's a vector, but we don't have anything like a magnitude that just a generic pile of particles can represent. So you need something else. And that something else is, I believe, waves, okay? So if we have a bell or anything, if you hit anything, it's going to have a resonant frequency. If you hit this, it's going to, if I had a glass cup, it would ring a lot better. But if you think about what happens when you hit a bell, see that creates a vector, right? Like we were explaining earlier today, that if you have the sun and you think about the light that's coming off of that sun, it forms a particular vector direction, right? Those photons coming off are a specific vector. And if you think, and we think that light is like a wave, right? So literally we have the waves, the wave fronts, the direction of the wave fronts determine a specific vector direction, right? And then just like a light bulb that you can make brighter or dimmer, you can have the wave, like let's say the amplitude of the wave can determine the magnitude. So if we have a generic particulate medium that can support a wave, then we can support a vector in that field, right? So the field actually is the particulate medium. What encodes that field is the wave. The wave has a magnitude and it has a direction. So that is what I think fundamentally encodes any field. The magnetic field will have this characteristic. The gravitational field will have this characteristic. And fundamentally, the electric field will have this characteristic. And I actually think all three of those forces are actually the same thing. And I explained that as, if you just start out with the electron, and what it is that it's just pulsing. It's got this, it's as if it were a bell and you're hitting it, right? So that sends out the negative electric field. The negative electric field is in fact just a high frequency wave that's coming off of it through the medium, which is just these neutral neutrons or whatever, okay? So the electric field could literally be substituted with like a light field, as if the electron were a light bulb. And it's sending out these waves in every which direction. And this is why the electric field and photon and electromagnetic field have extremely similar, I mean, they are actually identical, right? They're both 1 over r squared. They're both infinitely distant. The electric field acts exactly like the light field. Why? Because the electric field is a light wave, is a light field, right? Literally as if the electron were some kind of light bulb shooting out these waves all spherically around, right? And that encodes, like I said, the vector direction and magnitude, right? So that creates, say, electric field. And the gravitational field, my simplest incantation of that is that the Earth is just net charged positive because electrons are lost. And because of that, the Earth is a gigantically positively charged ball, and it's just very much like a balloon that you rub against your head. And we're very much like little bits of paper that are being picked up by the balloon. That's just, like I explained before, a reaction between the dipole matter, the neutral dipole matter, which makes us all up, and big giant charge beneath our feet. So really, gravity is just a overgrown case of static clang, is what it basically boils down to. The magnetic field is much more difficult to explain because it actually relies on the dipole nature of the neutron. So the neutron is not completely neutral. I think that there should still be a detectable positive and negative end to the neutrons. If you have two neutrons which are lined up like this, you send a charge through between those two charges because this is going to be positive, this is going to be negative. So it's going to be repelled from the negative and be attracted to the positive, and it's going to deflect when it cuts through those dipoles, right? So that is the reason why the magnetic field is actually just when the dipoles are all lined. If space has all dipoles all lined the same direction, then you shoot any charge through that alignment, it's going to preferentially deflect. So that's how I see what the magnetic field is. And that also has a particular vector direction as determined by basically the polarization, and a magnitude, which is like how many particles per cubic centimeter are aligned versus ones that are not. So, but that's basically how I see how the field is fully physically encoded. That unlike Bill, I don't have to appeal to God to say what that vector direction is. I don't think God determines that. I think there must be a physical particle involved in doing that. So Bill, what do you think? I mean, I'm thinking that in order to encode that field, there must be physical particles behind it, is basically my bottom line. It can't be God.
Well, the one needs a source for the field, but Winston Bostick and Arthur Compton, his advisor, who was a Nobel Prize winner, they did the most important experiments to determine the nature of the field and the structure of field solitons, which contribute to making elementary particles. And they showed that the strongest structure man has ever experienced is the soliton in the electric field. And this soliton is so strong that you can put it in the middle of a nuclear reactor. And the reactor will cause all the materials of the wall and the structure to come apart over time, but it doesn't affect the soliton at all. The soliton is much, much stronger than the field. Than the atoms and other elementary particles. So that's what you see. And also,
but I don't know that gets to this point about what make the field.
A magnetic moment and a spin magnetic moment. So it's got three kinds of fields. How can you explain that with just one particle? And in a pinning trap, you can take one electron in a vacuum and you can put it between the plates of the pinning trap, and you can perform all kinds of experiments on that one electron and measure the magnetic moment, the spin, and the mass, and the regular field of the particle. So that's associated with that particle. And so you're going to have trouble explaining pinning trap experiments.
Well, no, I don't have trouble explaining the pinning trap experiment because, if you look how these things work, the only way they can keep that electron in place is basically by balancing it between two other fields, which means it's in motion. Now, once you put an electron into motion, then you are no longer measuring the properties of an individual electron. You are measuring the magnetic field, which is going to have to be generated by any motion in that electron. Now, in order to be convincing, you would have to be able to measure magnetic properties of an electron which is absolutely stationary. And I don't believe there's any experiment that can hold or claim to hold an electron absolutely stationary. Really, the only way you can measure anything out of an electron is by actually moving it, because otherwise you really can't detect it. So the question is that are you measuring something which is inherent to the electron? I mean, this is why I have big problems with like the measuring the spin of electron in the Stern-Gerlach experiment, because you're not dealing with a single electron. You're dealing like with a whole silver ion. I mean, for God's sakes, that's very much different than an individual electron. My personal theory is if you did the experiment correctly,
in a spinning trap, you have one electron and you can measure its mass, its weight. You can measure all kinds of properties. If you had a media around it full of these particles, you couldn't do that.
Yes, you could. Why would you not be able to do that? If you're surrounded by
Because
a neutron field,
give it a unique value.
No, if you're surrounded by a neutron field, then really the reason why you can measure a mass at all is due to the interaction with that neutral neutron field. Because if space were, say, truly empty, then there would be nothing to resist an acceleration of an electron, and you would predict that, everything should be massless. I mean, that's actually the main problem with mainstream has, and that's why they had to invent the Higgs boson, because, there's no theoretical reason why anything should have mass at all. If there's nothing to interact, then everything should have zero mass. But if you have your electron and it's moving through this sea of junk, then there's going to be resistance to that acceleration, which is actually the definition of mass. So I would argue that we measure a mass absolutely tells you that it must be interacting with something, and that I think you would also agree that the mass is being an electromagnetic phenomenon, that we should be able to run experiments, and I think we do. I mean, we can change, say, the measured mass of an electron. If you send if the environment of an electron is like a net positive charge field, we physically measure the mass of the electron being different, right? The mass of the electron is not constant. It depends intimately upon the environment that it's immersed in, right? Now that's I'm pretty sure that's probably a shock to some people, that the mass of an electron depends upon its electrostatic environment, but it does. So that's a big clue telling you that mass is not an intrinsic property of the electron. It's a property which depends upon the environment it's immersed in. It's like if you have a ping pong ball and you run it through water, you can get a certain resistance. You run it through maple syrup and you get quite another, right? And that's actually the nature of what mass is. The mass is not actually a property of an inherent property of the ping pong ball, which is a constant that you measure the same everywhere. It depends on what medium you put it through. That's kind of what I would say. So I would say that if those kinds of experiments are preventing you from accepting, these ideas, I mean, those experiments do have to be explained, I haven't done it, but it would be my responsibility to show that the spin that they're measuring out of that penning trap is actually due to the motion of the electron itself and not anything inherent. Now, I could be wrong. When I look at this, maybe I'll go, oh, well, I guess there really is a spin, And then I would have to explain it. But my first guess is that that you're right, that if I think that an electron is just this like bell, which is probably spherical, but maybe it's not. Maybe an electron is fundamentally a sheet, and it's like hitting a tin sheet is what you're doing, and that the waves coming off of that thing would be definitely polarized, right? Whether you're hitting a tin sheet or a bell, the shape of the wave coming off of that thing would be very different, right? And maybe the spin that they're measuring is the two sides of the sheet or something, if they can in fact measure in asymmetry. But I could accept the electron being a sheet or a sphere or any other geometric shape. And maybe it's a triangle. I don't know. That would be an interesting theory to predict. I mean, this is kind of like how us, theoretical physicists work. Is that we're basically making up stuff, And Harry Ricker is always saying that my stuff is just all science fiction, and it's like basically all of our stuff is science fiction, right? It's something we make up in our minds as a story that makes sense. But it makes about as much sense as, say, the Star Trek transporter system. Yes, it's like we can have transporter system. You step into this box, it dematerializes you, and it rematerializes you on the planet, and all makes perfect sense. But it is in fact a complete work of science fiction, and it's not reality, right? Although maybe someday, maybe someone will make that happen, right? But it's just a matter of what's plausible. What experiments can you do? So based on, say, like I said, that's an example. Let's say that the penning trap shows, there's this asymmetry in there, and then I would go back and say, okay, then it's like a sheet, and we should predict that there's waves coming out, this way, and then very little out of that way, and then design an experiment specifically looking for that. And if you did that and it came out that the results were positive, then that would be very good evidence for the shape of electron being like some kind of sheet versus a sphere. It's perfectly sphere. So, but I see we got another question here from Stefan. So it says, Bill, can your theory predict pressure electric waves discovered by Nicholas Tesla and Podenklev? Scalar pressure electric waves. Podenklev, he did the gravity canceling experiments, didn't he? I don't know that him and Tesla had anything in common. Are you at all familiar with that, Bill? Let's see here. What happened to my connection? Let's see. I think we may have lost Bill there. Let's see. We got another comment from Duke, who says, so we don't need physics to describe this field. So in Bill's world, yes, he doesn't need physics.
And it means it's continuous for tremendous distances. And so that is an important aspect. So you can have waves in the electric field of various types. And you can have particles that are made of solitons. Solitons is a very long-standing wave in the electric field, and it's in the shape of a toroidal ring. And that toroidal ring has the equivalent of what we would call charge. It has spin and magnetic field associated with it. So all elementary particles that we know of can be made with these, and it turns out that the electromagnetic field has chiral symmetry, and all of the elementary particle structures have chiral symmetry, and so one can predict what they're going to be, what the complete setup to a certain energy level of all elementary particles is, and you can predict the mass, you can predict how it decays, you can predict the total spin, the magnetic moment, all of these properties of elementary particles and its decay modes and everything.
Yes, but Bill, you know what my least favorite physical shape is, right? The torus, the toroid. I hate that thing. I absolutely. I want to.
But
just
that's
go
what
out
we
and
see.
Stab it. That's what I want to do.
Yeah.
Because this. I mean, this is the big point as to what, say, electrons are made out of, right? So either electron is made out of something, right? So you're saying that the electron is made out of the electrostatic field, which is kind of a wrap up of this toroid.
The electron has 3 solitons in it.
Yes, and so it's like these three rings put together, and that's just something that I cannot accept. I cannot accept that. I cannot accept that an electron is made out of 3 things, because if it were, I'm pretty sure we would have found it by now because they've been
But
experimenting
we've
those
already
things to
found it.
death. No,
We've
not
already
really, not
found it.
conventionally.
See,
Not
you're
conventionally.
not an experimentalist, and you've now
Conventionally,
worked with
no
all
mainstream
kinds of
person would agree with you.
accelerators. Oh, the people who work with accelerators, they agree with me fine.
No, I don't think they would either. I mean, they don't. I mean, physically, you don't have to deal with electron being made out of anything to do anything with an electron. You just have to know that it has this mass, it reacts this way. You accelerate it, it does that. You know, that's really you have to know that, but you don't.
We can take an accelerator and we can, instead of making a beam of thousands or millions of electrons, we can make a beam of one electron, and we can measure what happens when it moves. We can measure that the mass of that electron changes. We can measure that the electron is giving off energy.
Yes, and none of that has to do with the electron being made out of anything. I mean, that's just empirically what we measure from an electron. I mean, and experimental results are experimental results. But the question is, see, this is why a toroid is my least favorite object in the entire world. It's a smoke ring. And smoke rings interact with the medium. And that, first of all, this is presuming that there is a medium. You can't have a smoke ring without mediums. And in which case, then you have to go and ask, well, what's the medium of the electromagnetic field? But, you know, then you have to say that that's God or something like that. But it has to interact against the medium. There's collisional forces in there. And that smoke ring cannot be stable over long term. I mean, it will dissipate and must dissipate. There's nothing to keep it going. As a smoke ring goes, it is dissipating energy all the way along the way. You know, it can last a long time, but it can't last forever. It has to be continually supplied, or there has to be something continually rebuilding the vortex inside that thing. And I don't believe there can be anything to do that. So that's why I just can't believe that the vortex is a stable structure. Now, I know you say you have experiments showing that the vortex that they created in these experiments is the strongest thing that you've ever created. And that may in fact be true, but that still might not have anything to do with, say, the actual electron, right? You know, if you could create a super strong torus that, like, you know, acts like the bullet and you could shoot it through the earth, that would be amazing, but still might not have anything to do with actual electrons. And this is, you always get into this, you know, chicken and the egg problem when you try and make particles out of some fundamental wave. And I have lots of arguments with people who say that, you know, you say it's made out of solitons, other people just say it's made out of waves. And I'm saying, no, you can't create a solid particle out of waves. It's much easier, I think, to start with what we do know. We do know electrons exist, okay? We may not know what they are, but we know what they're there, right? So instead of trying to say that the electron is made out of something, I'm arguing very hard to say that the electron is fundamental. Then all the other particles, like atoms, you can build them out of electrons, right? You don't have to say that the electron is made out of 3 solitons, and then you have to figure out what the difference between the electron and the positron is, and then you have to figure out how all of those things build protons and neutrons, and then you can come up, because you only do those 3 particles to build up everything. You have to explain electron, proton, neutron. Out of that, you can build like 99% of anything that's important, because everything else decays in a millisecond. So I would say that all those other particles don't matter, pretty much. But
protons very fast.
But I think it's just a much simpler picture to say that the electron exists, and the proton is made out of electrons and positrons, and the neutron is made out of electrons and positrons, rather than saying that we have to have all these really complicated pictures of, say, the proton. So the proton would contain at least 9 of these solitons, and you have to figure out, well, why does it stick together? What's the purpose of the neutron? All of that stuff. And I know that you can predict all these properties of all these atoms and stuff like that, you know, to 8 significant figures, and that's highly impressive. But it still might not be the truth. That the mechanical picture you're coming up with is too complicated.
It's simpler than what you're having, actually, because all you have is the field, and you have
no, you can't have just the field. See, it's because you cannot build anything physical out of the field. I mean, that's the whole question of reality. I mean, what's reality? What is this thing made out of, right? You're saying it's made out of fields, and I say no, it's not made out of fields. This is physical. This is hard. This is not a field. Okay, fields like waves. My main objection is that waves and things like toruses, when they collide into each other, they tear each other apart. They have to, right? That's what they do. There's nothing hard about them.
Winston Bostick did. He scattered solitons off of each other, and they did not come apart. They did not break. They did bounce off of one another. But
no, I think I did see those pictures, and they look like spiral galaxies colliding into each other, which means they did tear each other apart. I mean, that's what I saw when I saw those pictures. Like, yeah, that's what you'd expect. They just they go flick. They don't bounce off of each other. Definitely, smoke rings don't bounce off each other. You put 2 smoke rings together, they just tear each other apart. There's nothing left after they collide. And physically, when you think about it, that's what they must do.
The electric field has tensile strength. You can't cut it. And so when 2 things collide, 2 solitons, they're not going to come apart. There isn't any part to them.
No, there is a part to them. If they're a soliton like a smoke ring, then there's definitely a part to them, and that soliton itself is definitely cuttable. The electric field itself may not be cuttable, but the soliton is totally cuttable.
Soliton in air. Air has very little tensile strength, but the electromagnetic field has 10 to the 40th power tensile strength compared to air.
You give it 10 to the 40th power tensile strength, and it will tear itself apart even faster, I think. I think that logically is what's going to happen.
We don't see that in the penning trap. We don't see that in the penning trap.
Well, you see electrons in the penning trap. You're not seeing toruses in the penning trap. See, the thing is that's kind of a circular reasoning. So, you can't claim the electron to be the torus. So,
the 3 toruses in the electron. And by the way, the scattering experiments off nuclei show that the fundamental charge that is used to make nuclei out of is E/3, not E, the charge of the electron. So you've got to have something that's smaller than the electron that is being used to make protons and electrons and other things.
Well, I think you're referring to, that there's definitely 3 things inside of a proton. And,
but
currently...
we know what the charge is. We know the charge is E/3 or 2/3 E/3.
Well, I would once again disagree with that. I mean, I would have to go into those experiments and show that that's wrong.
You're saying I'm going to ignore the experiments that don't agree with my theory.
No, I don't ignore the experiments, but I think the experiments can be explained to say that, say in the proton, that there are not fractional charges in there, as quark theory would say, but that it's much simpler just to say a proton is 2 positrons and 1 electron. That's what it is. There's 3 things, so that matches the experiments, that there's 3 things in there. It matches the experiments because the proton is plus 1 net positive, which is exactly what you would expect from 2 positrons, electrons. So it meets all the experimental criteria. But it's just a heck of a lot simpler than saying it's like, 2/3 this and 2/3 that and minus 1/3 that. And it's like, no fractional free charge has ever been observed. And according to my theory, you never can observe a fractional charge because the charge field
can be observed. That's what the toroidal ring is, the soliton.
Yeah, but I'm saying that thing doesn't exist. You see, you can't justify the existence of the toroidal ring by saying that, electrons exist. That thing's a toroidal ring. Therefore, it must have a 1/3 charge. And no, you can't use that logic.
Experiments have been done to verify this. You're ignoring it all.
No, I'm not ignoring. I am not ignoring any experiments. You give me any actual experiment and I will totally explain it. I mean,
Well,
there's
just look up the work by Winston Bostic.
yeah, I looked up his work, I've read his work, and I don't see anything really positively pointing in the direction that you're saying. I mean, that's kind of a confusion to me that you're saying, go look at Winston Bostic, and it's like, yeah, I've looked at his stuff, and his stuff looks reasonable. He's got like these plasma experiments, and like that's all great, but you know, that doesn't point to the fact that an electron is one of these things. Is what I'm saying. I'm just not seeing the proof there. I mean, that you have to take a leap in order to make that whole thing. But you know, that's my anti-torus rant is what I guess I'm doing there. But like I said, you know, I'm just explaining. Well, I hate the torus. Okay, just wanted to make that point. Okay, but we got some more comments here. Let's see here. So Stephanie thinks stop decoding what's in God's mind. I guess that was kind of my point, that God does not want to keep track of every point in the universe. He really doesn't. He's got bigger fish to fry, right? Okay, I think. So let's see. So Duke is agreeing that yes, we need something physically, else we don't need physics, and religion is enough. Yes, we could just do that, right? We don't want to rely on just religion for our science. We'd much rather have something physical. That's why we call it physics, I guess.
Yeah. Well, that's why I'm using all these physical experiments and getting this data, but I'm showing the parallels between that and what the Bible has to say. In other words, I don't base it on the Bible. I base it on the experiments because that's the scientific method. You must use logic and experiments and come up with a unique theory that describes what you're observing. And but the people who are currently doing this in the scientific community now are using the existential philosophy of science, basically, which says we don't want to falsify any theory based on logic. This way we can have whatever theory we want.
Yeah, that's what we have right now. It's like you can completely, you know, ignore logic, like, you know, the logic of the theory of the atom, the Bohr atom. Logic would indicate that there's no way that thing could ever be stable, but yet we completely ignore that. Okay, that's just, there's no logical way you can, with using Newtonian mechanics, have that thing at all be stable. There's just no way that's possible. But yet we totally accept it. We say, yes, we have the nucleus, which is a tiny little speck, and we have all these electrons flying around, and we'll just totally ignore that. There's no way you can predict anything that would actually work in that whole thing. But it doesn't seem to matter, right? So we have a comment here, David. So there are three ways to make a field. We have ether, particles, and a lattice. Okay, well, I would kind of say that those are all kind of an ether, right? Ethers are made out of particles. Lattices are also all pervasive things, but all of them can do the minimum representation, what I'm saying. Minimum representation for a field is a vector direction and a magnitude. Anything that can satisfy that can satisfy the requirements for a measurable field. So Stefan has a question. Do you have any experiments going to confirm this? Okay. Any experiments say to confirm my crazy theory about everything being consistent of this field of neutrons? Okay. So my evidence is that we know that we can eject positrons and electrons from blank space. Now, this is typically called the conversion of energy to matter or a conversion of matter to energy, but I think that's a bunch of BS. That I think that the conversion of matter to energy would be a simultaneous violation of the conservation of energy and matter, right? And two wrongs do not make a right. So if you see a positron and electron being ejected from blank space, the more logical explanation is that they were already there, right? That's, if it were any other particle, that's exactly what we would say. We would assign it to be a neutral particle that's been injected in the experiment. But because it's a positron electron, we say it just was mysteriously came out of nowhere. But no. So, but that is evidence that, direct evidence that space itself is filled with a positron-electron field that we can eject positrons, electrons out of seemingly empty space. That's one piece of evidence. The other piece of evidence is the Lamb shift, which in mainstream, they say space must, in fact, be filled with a field of positive and negative charges in order to account for this slight shift that we see in the atomic spectra. Now, they call them virtual positrons and electrons, but I believe that there's nothing virtual about them. They are actually there. And that actually serves as direct evidence that space is filled with a positron and an electron sea. The other bit of evidence I would say is that, one of the main objections to this is that they're saying a positron and electron annihilate, and therefore your particle cannot exist. But if you analyze this in terms of like chemistry, we can see that what's going on here is actually a reaction. What we're getting out is binding energy, right? Like if we have water, we have oxygen, and we react them together, we get energy out of that reaction, and then the oxygen, the hydrogen disappear. Now imagine if you did that same experiment inside of a beaker of water, right? The people would say, oh, you've got oxygen, you've got hydrogen here. They collide together, they generate heat, and then it disappears, right? You can't find it anymore, right? Why is it you can't find it anymore? Because it's in the sea of exactly identical particles, right? That's why you can't see it anymore. It's not that it disappears, not that it annihilated. And just like chemistry, if you put energy in the system, you can separate out the oxygen and the hydrogen in an electrolysis process. And like I said, pair production is exactly that. You are adding energy, you are extracting the individual particles. So once again, this is all evidence to indicate that the main basis of my theory is that we're living in this sea of positrons and electrons, right? So that's all experimental evidence that all basically pointing to that. And I feel that an experimentalist, given that theory, should be able to conduct experiments to determine that precisely, right? I think it should be within our experimental abilities that if someone says, okay, the presumption is we're living in a sea of neutrons. The second, the question is, how can we precisely determine that? One of the experiments that I would propose is that we take a beam of positrons and electrons and we have them cross over each other so that they react. But the thing is that they would still have kinetic energy. I'm predicting that beam of positrons and electrons would in fact become a beam of neutrons, which would show once and for all that when positrons and electrons react, it's not an annihilation. They're actually creating neutrons, right? So that should be something we should be able to do, and conclusively determine that we do in fact live in a sea of neutrons, right? If the annihilation doesn't actually exist, if we can detect the particle after the reaction point, that would be one way of doing that. So that's some of the physical evidences that I think that we have, and other theories have to explain. Bill's experiment has to explain how pair production works. If it's,
no problem, because you just have to. And this is what Arthur Compton and Winston Bostic showed. You have to put some energy or ripple into the field just right to make the soliton, and then from the solitons, the simplest particles you can make are electrons and positrons. And
but it has to be just right. I mean, in order to make a smoke ring, you need a very complicated device, a barrel with a diaphragm, and it's very difficult to get it to actually do that thing. That's very complicated. I think it's a lot simpler just to say that where did the electron, the positron come from? They come from they were already there. And why is it that it's always a positron electron? If it were this special energy, then you'd expect, well, you could just get a bare electron, and there's no reason why you would not ever get a bare electron or a bare positron. It's a amount of special energy in special situation. You can always create one of them. But if it's ejecting out of a bound state, then you would expect only are able to do it only if you get both the positron and the electron. That's the only way to make it visible, right? That's the only way. So I think it's just
have you ever weighed
physically,
positrons and electrons and see what you observe? You
see pairs.
You see a pair and they're decaying. They're giving off energy as they get closer and closer together because there's nothing to keep them apart.
Yeah, there's nothing to keep them apart. And when they collide together, they eject out a piece of energy, a gamma ray, and in back to back, which is exactly what you'd expect for two things colliding into each other. Because literally, the gamma ray is less like the clap you hear going out.
But it's
that
not
way.
a particle, that's mass. What happened to the mass?
The mass doesn't change. I believe in conservation of mass, absolutely. Conservation of energy, absolutely. There is never a conversion. Never, ever, ever. Conversion is a violation of conservation of mass and energy. And like I said, two wrongs do not make a right. All right. That energy is the energy of the collision. That's why the speed of light is in that E equals mc squared. You ever wonder why the speed of light is in that equation? It's in there because that is the speed limit that these particles can collide into each other at, right? That's the maximum speed they could ever attain in real physical space. That's why c is in there. It's not some other constant. It could have been any other constant, but it isn't. It's the maximum speed attainable by any particle prior to collision. So, and then it's just adding the kinetic energy of the particles together. 1/2 mv squared plus 1/2 mv squared, where v equals c equals mc squared. And the math is just that simple. That's so it's not a very complicated thing. You know, a third grader could do that math, right? 1/2 plus 1/2 equals 1, right? That's how I see that. Let's see, we've got some other comments here. It says, yes, binary mechanics chooses the lattice option is one thing. I personally don't like the lattice option because it takes whatever those particles are and they fixes it into this cubic, lattice. So the particles are fixed. But the problem is that for the magnetic field has to exist simultaneously with the electrostatic field, right? And it has to represent a vector. Still, now the vector can't be represented by the same electrostatic wave front vector. Those two can go at completely different angles. So the magnetic field vector has to have a physical different representation. And in order to have that physical different, those particles have to be free to move in space. So, I have a dipole particle. The dipole itself determines a vector direction, right? So in addition to a wave front that might be going this way, the dipoles that are representing the wave can be pointing in different ways here. I see we have Nicholas Skype adding here. So if you'd like to make any comments, give us a wave or something. And you're live with us. But the reason why I don't like the lattice is because I need the actual particles of the space to represent that vector direction for the magnetic field, right? So like Epola is very similar to my theory in that they do think that space is filled with positrons and electrons, but they fix it into a fixed lattice, which means that the actual dipole direction is not available to represent the magnetic field direction. But in my theory, the dipoles are free. They can point in any direction they want. Therefore, they can represent another vector direction. So we have a comment here. Ether particles stay where they are. Particle model, particles move. Well, I'm not 100% sure, but if you have a fixed lattice, then I go yeah. They stay where they are. But like I said, that's kind of the difference between my lattice, the lattice model where those things are kind of fixed in space. They form like a fixed grid versus a model where it's more like a fluid sea, which is what I'm thinking, where the particles can move around into the particles. The sea itself could move like a river, right? But you could also have things like bullets going through that sea. And so David has a question. So Bill, do you believe in an ultimate particle? I know, I'm thinking not. I'm thinking you believe ultimately in the
Well,
electrostatic field.
some people might say that the soliton is that particle.
Yeah, so your soliton might be...
The soliton cannot be destroyed by man with anything that we know currently, because it's the strength is so great due to the tension in the electric field. But it's not an elementary particle because it isn't a particle by itself, as far as we know. We've never observed it. So they tend to group together with chiral symmetry. And so they have like 3, 5, 7, 11, 13, 17, 19.
Hey, we got another question for you, Bill. We're kind of running out of time here, so I want to get to people's questions. He says, included you are creationist, which I believe that's true. Says, can you solve the problem of distant light in young universe?
Yes, I have worked on and published many papers on these articles, but they're not in they're in creationist type of literature, not the scientific literature. When I talk about these in the scientific literature, I get fired from my job.
Now, so you work with Roger Wright in here. We get a comment here. It says Roger doesn't support waves, yet the soliton is a wave. Although I don't think the soliton is a wave per se, any more than the smoke is a wave.
It's a structure in the electric field which has tensile strength.
Yeah, I think that's the solution. It's not a wave; it's a structure, right?
A structure. It's a, well, you could say it's not the normal kind of wave we're used to. It would be like a smoke wave that never disappeared.
Yeah, like a smoke wave that never disappears. See,
so it's so strong, nothing can break it apart or stop it from continuing on. And that's what Winston Bostick did. And I'll give you an example of something we made. We made a jet engine. At MIT, we converted an old jet plane, took the original jet engines out. We put a soliton on a
you made the super amazing jet engine, but the question would be, is if it was so successful, why don't we see that?
Into this soliton. We're able to get it to millions of degrees, and then we let air into that, and it makes it like a jet engine. So we took that, we made a jet plane with it. We invited NASA, we invited the commercial airlines, and we invited the military to come and observe. We took that jet engine plane with no fuel, just this soliton, which was heated up using things like this nanotech crystal, which can generate a great deal of electrical energy from the radiation in space. Anyway, we took that and we did a flight all the way around the Earth from.
Well, I guess maybe that might be relevant to this comment here, where he's
fly around the Earth 2 hours.
Yeah, well, he's saying that you should have to make some prediction and propose experiments. And what you're saying here is absolutely fantastic, but considering our 737s don't run on this engine, it makes it a little bit hard for us to believe, I suppose.
Wait a minute, let me tell you what the results were. We demonstrated it to NASA, and NASA said, we're not interested in that. We only want to spend billions of dollars to go to the moon and to Mars. And how much would it cost to go to the moon with your equipment? And we said, about $8,000. They said, no way. We don't want.
So once again, we're not.
We want more money. That's what they said. We talked to
your solutions are too cheap, Bill. Right?
That's right.
But it's just a little bit hard to believe. I'm just saying,
we asked the commercial airline, and they said, no, we don't want to use this because they said we get tax-free space for all of our airports because we use fuel. And now you're asking us to give that up, and we don't want to do it. And we don't want to we don't want to. We only need a few planes. We don't need all the planes we have. We can't charge as much money as we are making right now if we use this technology.
Okay, we got another question
And
here. How do atomists explain electromagnetism if there is no field? Well, I don't think anyone would say that there's no field. I mean, even atomists would say that there's fields. So.
The question is, how do we measure charge? And the answer is, we use the field to measure charge. And so when we write down Coulomb's law and we put Q in there as a constant for the charge, that is a mathematical approximation, which works fairly well, but it's an approximation. It says there's something called charge, which we have invented, which we have never observed. We can't see it directly. We can only see it via the field. And so that's what we have done. And basically, when Oliver Heaviside took over after the death of Maxwell, he was representing a group of people that did not like everyone calling the field the Spirit of God and stuff like that. So he wanted to do everything in terms of charge and these other approximations. And he got rid of two of the empirical laws of electrodynamics, Lenz's law and Lorentz's law. And as a result of that, we had to invent quantum mechanics. We had to invent special relativity theory. And but you would not have needed to invent those if you had kept the original set of Maxwell's equations and solved them simultaneously. And that is what I do in my book, The Universal Force, Volume 1, which is available on Amazon.com and many other places.
Okay, so now I see I've got the next series of comments are about how I'm moderating here. So it says, so I'm not sure exactly where I was wrong, but please preface your comments with "in my opinion," and like I think that was pretty obvious. You know, if I were to say that, then it's like everything here is in my opinion, not unless I'm expressing the results of an empirical experiment, in which case it would not be my opinion. That's just how the experiment works, right? But you know, I think that would be pretty obvious. And Harry is complaining about how I'm doing nothing but giving my silly, uninformed opinions here. But clearly, we have Bill over here. Bill is also giving his uninformed, informed opinions here. So glad to have you here, Bill. So
my work is based on logic and experiment. I'm following the scientific method by Isaac Newton, which is to combine method, experimental results, and logic, which is what I am doing. And so I started out by solving the 6 empirical equations of electrodynamics.
We know how to do that. We do have some other comments,
Maxwell
Bill.
never did that. No one else has ever done that as far as I know. And when I did that, guess what? I discovered that the fundamental structure that electrodynamics empirical laws give is the soliton, which was confirmed experimentally by Arthur Compton and his last graduate student.
I don't like the soliton because logically there's nothing to keep that thing together, right? So logically we cannot use the tensile strength. Doesn't help you because that doesn't defeat the problem that it interacts with its environment. It must lose energy.
In terms of structure.
See, this is where I think you're not following your own. You're not following your own philosophy, which is you have to use logic. Logic has to determine that thing must be long-lived, and logically that can't be.
Empirical equations of electrodynamics, you get that the soliton is the structure,
and that structure cannot be stable logically. So therefore, that cannot be right.
Experimentally, it is stable. And
no, experimentally, there's no way you can experiment on a single electron.
So anyway, that's.
But I mean, that's logically, and logically, the soliton cannot be stable. I mean, the only thing you can say is that, oh, we've experimentally measured it to be stable. Logically, it's got to interact with the thing that it's made out of. It must lose energy. It must not be stable.
It's not made of anything. It's just a structure in the tensile strength electromagnetic field.
Yeah, but you admit it's like this toroid thing. That's a physical structure.
It cannot be subdivided. It cannot be cut up into pieces.
All right, so we have some other comments about the moderation, but now I would invite you that the only reason why it's an opinion between me and Bill is because we're only the two who are volunteering to speak. So otherwise it'd be like this. And it would be very boring. So I think it's much better that, you know, I'm talking and Bill's talking and I'm keeping the conversation going. And Franklin, can you see him saying that everything is an ether? That is not correct. Well, once again, that's in my opinion, I suppose. Ether particles transmit waves through kinetic energy and basically stay in the same area. Yeah, I agree on that. Other models do not do this. Well, you know, this is what we're here to discuss. Of course, I have my own opinions. And I never say experiments are wrong. Never, never, ever. Every experiment, physical experiment you show me, I need to explain. I never say experiments are, say, wrong, like the penning trap. I believe what's wrong is the interpretation, right? So you've got experiments, you've got results. Now, might be consistent that an electron has, say, a measurable spin in the penning trap, but that could be a misinterpretation. Just like if you have positron, electron, you react to it, you know, the conclusion is it annihilated. That is, once again, an incorrect interpretation of that experiment, right? It's not that I'm saying that annihilation doesn't, you know, the reaction of the positron electron doesn't happen, but I'm saying that there are other explanations other than them disappearing to explain, you know, why the gamma ray comes out and why you can't see them afterwards, right? Different interpretation. I don't ever deny any empirical experiment ever, okay? I have a responsibility for explaining those. So I guess Cornelius is complaining that David's ether particles, if they exist, must be integral parts of each other, and there'd be no possibility of tension or attraction. Well, I don't know. That would be something that David would have to defend there. And once again, I would love you to come into live.naturalphilosophy.org and join the conversation, because otherwise it's just going to be the me and Bill show. And that's kind of what I'm not really liking about StreamYard, because it's not really inducive to getting people to just get in the conversation. And therefore, I have to just read these comments and just kind of react to them and have conversation that way. So, but Kimbo said that the Big Bang is basically correct, and the Planck epoch, the total matter in the universe was blah, blah, blah. Where then does this leave the idea that electrons and positrons have no precursor? Well, that would leave well, first of all, I'm not sure whether the Big Bang actually occurred. Once again, this is in my opinion, right? And Bill, you can chime in if you'd like. But I can neither confirm nor deny the Big Bang because I was not there, right? And I believe that the positrons and electrons have existed, always existed. If you're interested in my take on what God's position is on this, I have a whole paper that basically says that we are possibly in God's computer. And what is an electron? It's actually a bit of programming code which says this is what an electron does. And physically, there is nothing physical about an electron any more than in the Pokemon game, there's, you know, Pikachu, right? It's like, what's Pikachu made out of, right? Pikachu is made out of programming, right? And ultimately, electrons and positrons are made out of programming. So I believe, you know, God may have this computer and we're running in it. And the reason why we can't find out what an electron and positron is because it's literally a piece of code, just like Pikachu in Pokemon Go, right? You can never find out what Pikachu actually is. It's not physical, right? But in the game, he's totally physical, right? So Jim is asking, do you believe that photons are solitons of the EM field? Solitons? I don't think so. What do you think, Bill?
A photon is a wave in the field, but it doesn't have. It's not a soliton. It doesn't have extreme lifetime and strength.
Yeah, I wouldn't think so. So
It's
that I think Corey is
a
agreeing with
weaker
you
type
that he's saying that soliton is not a standing wave. It's a structure in.
Yeah.
It's a definite long-lasting structure within the electromagnetic field. It's not a standing wave like a wave in a violin string. It's definitely not that. I don't think.
But it can be created by perturbing the field.
So charge is a pattern of energy in the field, not separate from it. Well, I would agree with that.
Yeah, that is the basic idea. Is that the pattern? If you want to explain it mathematically, the simplest way would be to use charge, and you could get empirical equations that explain many experiments. Not all experiments, but many experiments. And so that's how we got this idea that the charge was there and that we made charge the source of the field. But in reality, the field is supporting this structure called soliton, and it's that structure that that causes the field of the soliton that is not defined like a physical ring, and that's nothing else. The field lines go to tremendous distance from that. So it's not like a billiard ball with a sharp edge on it. It doesn't have that feature. But
I think the electron is a billiard ball with sharp features. Just to let you know.
Yeah.
But
now this is interesting. We have George Dukas, because it turns out the work of Moses was not only preserved in the Egyptian and Greek culture, but also the Indian Jains preserved it. And this is a result of that work by Moses. They call it.
Yeah, a lot of ancient.
Pronounced a little differently in Indian, but
I think this matches more closely my philosophy, which is that you've got to have these two waves. One of them represents the positive charge field. The other one represents the negative charge field.
But see, he has here all of space is made of that stuff. So, anyway.
Yeah, and I would agree. See, I'm saying all space is made of positrons and electrons. So that's exactly what I'm saying. Now, here's a philosophical thing here that I talk about computers, but the computer has to be made of material substance. So what's God's computer made out of? Well, that's made out of the real substance, right? The real electrons are made of God, so computer makes it. Yeah, you can keep on going down that rabbit hole. Yeah, God's computer is made out of God's stuff, I guess. And that would be the real. It would be like we're in the Matrix, right? If we're in the Matrix, a movie like the Matrix, it's like all of this stuff in our head, all the stuff we're experiencing, it's not real. But our bodies physically are sitting out in the Matrix pool and plugged into wires, and that's what's real, right? So, it may be the actual electrons exist there, and those electrons are made of solitons, actually. I don't know. But we've come to the end here. We've kind of exceeded our hour, but I thank everyone for participating. So I see we have 11 watching out in YouTube, so thank you for showing up in StreamYard, and we have 3 people here participating in the room, so that would make a total of like 15, which is about the same as what we were getting in Fuse. So I'm glad to see that we haven't lost watchers. But thank you for participating, and that will do it for this episode of the John Chappell Natural Philosophy Science Chat. And if you have any comments, please send them to me, franklinwho.com. If you think I was talking too much, or we are trying to get used to this new system here. So if you have any comments, good or bad, let me know. We're going to try and compensate as much as possible. And I would invite more people to come into the live room to chat and to, say your piece so that, we can have a better interaction, because this is a chat. This is like a Sunday coffee room thing for you guys to talk. I know a lot of you just like to listen, but this is here to discuss what your questions are and what our answers are. So that will do it for today.